Thanks, Luke. Good to see everyone. Students are getting younger every time I give this talk, I'm sure. So, yeah, straight on. So this is on wet deposition, but I thought we'd look at processing of the entire atom step, sort of the atmosphere step, and how the sequence works, because that's extremely relevant in this case. And then we'll do how we treat wet deposition, trace gases and aerosols in UKCA. And then I'll do a little bit on aerosol budget analysis, which might help. But the main thing about wet deposition is it's a black art. And that's because you're treating a huge range of sizes. We're dealing with aerosols on the sort of micrometer scale, up to synoptic systems on the hundreds of thousands of kilometers scale. And in the model, there's a lot of processes which are difficult to get hold of, like what is the cloud lifetime, or what is the airflow through a cloud, and they're quite hard to get exact numbers from. So that's why wet deposition is quite tricky and always needs further work. So this is a very highly simplified sequence of calls in the atmosphere step, and you have atmosphere physics 1, and within that is the large-scale cloud and precipitation schemes, and those at the moment furnish data for UKCA in the terms of precipitation and cloud amounts that we use and a few other things, cloud liquid water. Radiation, UKCA, if you turn on the right switches, will effects of the optical depth and the gas phase, things like methane will affect that. Then you have tracer and dynamics advection. Obviously, that's critical for UKCA. In Atmos Physics 2, convection is there, and within that is the aerosol removal in the convective plume, which I'll call plume scavenging here. Boundary layer, an important process as well for UKCA. Diffusion, the solver, the main solver of the model dynamics. The Carriol ozone scheme, which is normally not turned on if we have running UKCA. Tracer conservation, critical. Classic won't be turned on for you. And then we have the bottom two, which is nudging to imported fields, which can be highly useful. And then the UKCA call comes last. So that gives you a little idea of what else is going on. And then wet deposition. Obviously, there are trace gas and aerosol tracers which are highly soluble. And wet deposition for these species can dominate over dry deposition for those species. It's important to realize there's a lot of uncertainties in the wet deposition, partly provoked by how good are the simulated precipitation fields and things like cloud amount that you need, and also by the, I'm tempted to say, oversimplified treatment of wet deposition of the tracers. And in some ways it has to be oversimplified, because if we don't have the data to drive a more strict model. And there's a couple of references. So let's look at the soluble tracers, the gas phase soluble tracers, handled in UKCA for both the large scale and convective precipitation. And it's important to realize that is wrong for the convective precipitation, because what happens is the scheme in the unified model can loft your soluble tracer a long way in the atmosphere without any removal by precipitation. And that can lead to higher concentrations in the upper troposphere, for example. And an attempt to introduce plume scavenging for gas phase tracers is in progress. Well, so was my train until we got to Newbury yesterday, but it's a problem that we've been diverted off that into other things, but I hope to get back to that fairly soon. With the soluble aerosol traces, the large-scale nucleation scavenging is done in UKCA, so impaction scavenging is done in UKCA using, obviously those are using data imported from the precipitation schemes. So impaction scavenging is aerosol speak for the wet removal due to rainfalls, rain intercepting the aerosol particles. And there's an additional process which I call plume scavenging. So that's called from within the convection scheme. So where there's updraft and precipitation formation, then we remove tracer. So plume scavenging for the aerosol tracers is the default scheme. I don't think there's any way of calling it off from the Rose Edit panel, and you wouldn't want to anyway. And that's because what we found was the aerosol optical depths, if we didn't have plume scavenging, were very high, or unrealistically high. So that's how so that's why it's the default scheme. And very early models of UKCA didn't have plume scavenging, but they suffered from excessive drizzle. Constant drizzle over the ocean regions was quite characteristic, and that was caused by faulty assumptions in the precipitation scheme, because all the rain that's formed was falling out over the time step, even though it would have taken longer time to fall to the ground than the time step. So that means that in GA6, I think, we now have a prognostic rain scheme, which means that the rain is able to carry on from one time step to another. An important caveat in all of this is we don't have re-evaporation of dissolved traces in the precipitation yet. Now, obviously, the precipitation, if you sum up all the precipitation formed by the model, you get more than you get than hits the ground, because some of it evaporates on the way down. However, that's not yet treated and is an important is another problem that we've got to write in. Practicalities, there's a chemical definition file called UKCA Chem Master, which defines the soluble species. And you can see on the right-hand side of that, there's 3 integers, and which, if they're turned on to 1, denote dry deposition, wet deposition, and emitted species. So that's nitric acid, and that's got the 1 turned on for wet deposition. So the fraction of that tracer contained in the cloud droplets depends on the effective Henry law coefficient and the cloud liquid water. The dissolved fraction is also required for any aqueous phase chemistry you might do. And the Henry law information is in the same block of code. Now, the effective Henry law coefficient is a function of temperature. And it's important to realize that some species, for example SO2, dissociate through equilibrium reactions within the cloud droplet and can hence dissolve more than the direct simple Henry law will allow. So SO2 will dissociate to form HSO3 minus, and that will dissociate to form SO3 2 minus. So although the Henry law for SO2 is quite small, a lot of it gets dissolved in the cloud droplets, and the treatment of that is and that is why there's 3 sets of Henry law information to allow for that effect. So removal rate of the dissolved trace gas is assumed proportional to the rainfall rate via an empirical scavenging coefficient. And Fiona O'Connor described that tracer removal in her paper, which uses nitric acid scavenging coefficients for dynamic and convective precipitation from Penner's work, and then scaling that by the dissolved fraction of each species. So that's a scavenge coefficient times the precipitation weight, where the diagnosed precipitation is rain plus snow. We haven't got a separate treatment for snow and ice in this model. Large-scale precipitation assumed to occupy the entire grid box, but the removal rate for convective removal is multiplied by a grid fraction. To add a soluble gas phase species, then you have to add the species into the Stash Master A. I gather you've had a bit of experience in doing this. Setting the option code as per the instructions, changing the number of gas phase traces and the number of soluble traces in UKCA setup chem, and adding a Henry law entry. Now, evaluating wet deposition, Fiona O'Connor and of course other people using other models used a radon radioactive decay experiment. Radon decays to lead-210, and this can be, the lead-210 can be removed, giving you a deposition rate. And although the radon emissions themselves are highly simplified, that gives you some idea of how good the wet deposition is working. And there's details of a data set of wet deposited lead-210 in that reference there. She found that lead-210 concentrations were in good agreement with the observations at some sites. However, UKCA and other models underestimate lead-210 at the South Pole. So you can look up Fiona's paper to give you an idea there. Wet deposition of the aerosol particles consists of nucleation scavenging, where particles which are activated act as cloud condensation nuclei for droplets which then form rain. We do have an activation scheme in UKCA used for secondary cloud effects, but we don't use the fraction of activated particles from that scheme in the nucleation scavenging, because that engineering hasn't been done. There's also an in-cloud impaction scavenging where aerosol particles are collected by impaction with cloud droplets, and that is not included in the model, probably because it's of lesser importance. And there is below cloud impaction scavenging where particles are collected by falling precipitation. In nucleation scavenging, activated particles are incorporated into cloud droplets where they act as cloud condensation nuclei. The scavenging schemes use a simplified approach rather than being coupled to the UKC activation, which I've just said. A critical wet radius, particles larger than the critical wet radius, which is defined as 103 nanometers, is set in the routine UKCA rainout. And this then gives the fraction of number in mass in each mode which are dissolved if the cloud is present and becomes susceptible to wet deposition. In practice, only the Aitken and accumulation modes are affected by the activation radius, as none of the nucleation mode can act as CCN, whereas all of the coarse mode does. There are scavenging fractions which can be set to either the default scheme or the EC Ham model scheme, and they largely are the same apart from the modes which are insoluble. So normally we're using insoluble modes as you effect with zero, set to zero, but EC Ham, for reasons best known to itself, uses real numbers for it removes insoluble mode as well. And the aerosol is then removed at the same rate as the cloud water itself is removed as precipitation based on diagnostics. And those diagnostics include the autoconversion rate, that's the conversion of gas phase, water vapor, into rain, riming, so that's the formation of ice and snow, and then those those terms are, and then there's accretion, which is the interception of a small part of fog by rain, essentially by cloud droplets by rain. The terms are all added together before being passed on to the nucleation scavenging routine, and the removal rate is multiplied by the liquid cloud fraction and an assumed fraction of the raining portion of the cloud. Sorry I'm reading this, but that's the only way you're going to get anything. For very low liquid water contents, a fixed removal timescale instead. Below 258 K, all insoluble modes are also susceptible to wet deposition. As I said, we have introduced a convective plume scavenging routine based on work by Zach Kipling when he was at Oxford. And this is called From Within the Convective Uplift. And so is done at the same time. And applies only to the 6A or 5A schemes. So Convec 2 calls UKCA plume scav. The only problem with this is we don't know the fraction of the aerosol, the Aitken mode aerosol, which can be activated, even if we know the scavenging radius. So we have a simple fraction there, and that's because we only got the tracers. We don't have the ancillary information to work that out as we would do in the aerosol scheme. So the entire tracer array is passed to the routine, and logic is required to identify the relevant tracers, which we did get wrong at first and corrected at 10.6. So I hope you're using up-to-date code. Scavenging coefficients are set in that routine for accumulation coarse modes, and the Aitken mode as well. That's basically repeating what I've just said. There's now diagnostics for plume scavenging, which, because we couldn't work them out in a 3D sense because of the uplift, without putting a lot of code into convection scheme, which was frowned upon, they're only two-dimensional. So we take the column before and after and take differences, and that gives you the total deposition. And that's the impact of plume scavenging. So the one on the left is a no plumes one, and the one on the right shows the difference between the standard case. So the difference is something like 50% of the mean. So obviously a huge effect if we don't have plume scavenging. Below cloud impaction scavenging, I'm not that familiar with. It's based on the collection efficiencies for differing aerosol and raindrop sizes, where the raindrop sizes are assumed to be distributed into 7 bins using a well-known distribution. Aerosol modes are treated as monodisperse, i.e. they have one radius. The collection efficiencies are set up in those modules, and there is a bug fix version. I don't think that's still in the short-term logicals name list, I think. Yeah. So that will get fixed eventually, but it's best to use that. There is specific below cloud impaction scavenging for snow, and that shows you the power law implementation. But the coefficients used by Wang, who described that scheme, for the coarse mode aerosol were found to be too large, and we have reduced them. Evaluation of aerosol scavenging. Zach Kipling compared a version of the UKCA model without plume scavenging to a version with plume scavenging using the black carbon aerosol measurements from the HIPPO campaign. So both the black carbon burdens and the vertical distribution were shown to improve, I might say improve greatly, against the observations when plume scavenging was included. And as before I've said, we've got very unrealistically large aerosol optical depths, which that's a widely available measured quantity before we had plume scavenging. So these are the caveats which I've said on the way, but just to reinforce them. So we're not doing any re-evaporation. Plume scavenging needs extending to the soluble trace gas species. That's, at least in branch stage. Better treatments and diagnostics needed to describe the subgrid scale. That needs revisiting. And the gas phase treatment of removal by frozen precipitation probably could be improved. And I would say sometimes you read papers which describe parameter uncertainty, and for very important species the parameter uncertainty of wet deposition is quite small, because almost all of the species like nitric acid is already in the cloud droplet, so changing the fraction doesn't really, you're dealing between 98 and 99%, so that doesn't change things very much. However, when you're missing processes like re-evaporation, that could change things quite dramatically. So and there's also defects in the precipitation scheme. So it hasn't had enough attention, is what I'm trying to say. In order to sort of assess how the model is performing, or how the aerosol model is performing, various people, I think Graham Mann wrote the aerosol model glow map, including all the 3D diagnostics of each process. So there's flux diagnostics. And Nicholas Belluin and other people have created IDL routines which analyze those fluxes. And we'll just go through what this does. All of the diagnostics are three-dimensional apart from the plume scavenging. And analysis of these fluxes really can reveal what you are doing to a model if you make a change. So I do urge you to turn them on. Luke and I have set up the IDL analysis scripts on various machines, and I don't know whether I've written this, no. Essentially, if you go into Rose Edit and turn on 300 diagnostics, it takes you half a day. Don't do it. There's a file which you can just add to one of the Rose output files, which turns on them all in one blow. So adding the fluxes is much easier now. In adding the diagnostics into the model setup is easy, and then there's a there's a README file attached to that sequence, and some IDL files which you'll probably have to hack a little bit to point to the right place. And just go through what happens. This is these are I've chosen accumulation mode sulfate. So this is annual production. So there's a little bit of primary emissions, but in cloud oxidation of SO2 dominates the sources, and there's some minor sources from other modes essentially. But when it comes to the loss, dry deposition, a minor term, and the nucleation and plume scavenging make up sort of 80% of that loss. And the other thing you can check is whether your budget's balanced. In this case, they do. And on the right, there's the loss lifetimes in days, and they're 10 days each for nucleation scavenging and plume scavenging. So do have a go at the aerosol budgets, and indeed at the gas phase budgets, to show what's going on, because they are very revealing.
Okay. You can't run IDL on Archer, but it would run on Jasmine or on Monsoon.
Yes.
It's just because of the licensing.
Yes.
Yes. But if you've got IDL at your own institution, you can copy those scripts back and run there. And that would be fine.
Okay. How's the time going? Loads of time.
Wrap it in half
I know, I go through those too quickly, but it's probably good.
Are there any questions? Yeah,
so Colin, you talked about the dissolution of compounds such as SO2, which is pH dependent.
Yes.
Does the model compute a droplet pH?
We don't compute pH. I did it in StockM and then came to realise that many of the species that contribute to pH weren't in the chemical scheme we were running. So like most people, we assume a value of the pH. But it is an important point. We should try and estimate it, but without things like carboxylic acids, then I think it's a bit pointless trying to do that. It'd be better to base some variability based on the measurements of cloud I mean, in highly polluted areas, I think possibly you could have a stab, but beyond that, because it's essentially the strong acids, but there's a lot of other acids which we don't have. And there's things like calcium, for example, that we don't have. So I found it, I sort of thought it was a bit naive to try and calculate the pH, so set it at a value, but it is part of the uncertainty of the model.
At the back.
I was just a little surprised at the size. Sorry, I was surprised at the size of the rainout critical radius. It seems really large at 100 nanometers. Do you think that would affect the sensitivity of the model?
I don't know. I didn't write it. Yeah, good point, but I'm not sure what to say. I think you better read the reference that's in there.
Any other questions? Okay, well, we'll thank Colin.
I'm going to have a little chat about model development and how we would go about it.
A little bit lower. There we go.
If you open a ticket, other people can see what you're doing, and you can use it as a notebook, so you can add the branches you're using, and that's always the first thing to do. The next thing most people do is to start hacking the unified model, open a branch and hack the Now, that has to be done at some stage, but you might consider offline modeling. Essentially, if you're working with one routine and you want to make a change to it or add a routine, then make sure that it works with simple inputs. And for example, if you've got a new function for say a rate coefficient or a new function for impaction scavenging, you can confine it. If it's confined to one routine, then build what's called a test harness. So it's a simple routine. You've got, if you've got temperature, let's take a rate coefficient, you've got temperature, humidity as an input. You can vary those throughout their range and see if the function you're getting is the one that you wanted. Very simple case. You can optimize, you can have a go at optimizing the Fortran, you can it's so much quicker if you can do that. So many times people have added code and only after 6 months they've discovered there's a hole in it, or the function is discontinuous or something happens. So it's a good idea and much more efficient. So you got through this step. And there is a chemistry box model. There's a simple, I wouldn't use it as a research tool because it doesn't have any details like boundary layer depth. It's just a box model for the chemistry. It's a very simple driver and it can have the same routines as in the So you can again investigate simple cases. You can initialize the model, no emissions, and just see how the concentrations develop over time. And that's again can be compared. There are various papers which describe that sort of modeling. Again, that's an easy thing for you to do. The first time, if you're happy with it, open a branch. I don't know whether you can do this. Can you use RowStem?
They can't use RowStem on Archer. RowStem works on Monsoon.
Works on
Rose
one
stem works on
Okay.
the virtual machine.
Right. The first thing I do when I'm happy with my branch, I don't test it, I run row stem. So if you issue a command, oops, lowercase, that will run hundreds of tests. If you've done something silly like overwrite some part of the then everything will fail, but most often you will find differences. What that does is run applications like the strat-trop model, nudged strat-trop, air quality model, and the coupled ocean atmosphere GA7, which is the prototype Earth system model. Will run loads of stuff and it will compare the output to previously known output, and if they don't compare, then you'll know. So you'll know how the changes have affected the model, and you'll also get exposed to a variety of Fortran compilers which will complain, and it will tell you errors which you might not get if you just run one Fortran. And then, only then, would I start to have a suite and develop change and find out what is happening. So that's how I would approach the problem. Paul?
You mentioned chemistry box model 0.3. Does that mean there's a box model for UKCA that we can use?
Yeah.
Where do we get it from?
There's a couple of different flavours of it, so I think you have one that you use.
I've got one.
Scott Archer-Nichols here has one that was developed from Christina's work.
And are they both suitable for version 10.9?
Well, I don't see why not. But
There are some differences though. I mean,
Yeah.
it would be nice to be able to drive UKCA from the trunk with an external driving routine. And I think that's something that we'd like to do if we have the time to do it.
Yeah.
The problem is the one that we use here is based on 10.1 and is diverging more and more from what it is like in the trunk. I'm not sure what your type is at, Colin. But
I think I developed, I've got a 10.7 version.
right, so I think probably what we want to do is try and, bring them in, and it'd be good actually to make a row stem test, which is the box model from the trunk. If we could do that,
Yeah.
then that would be even better.
Yes.
But it's a very good point there.
That would be really helpful, Colin. If you could make your 10.7 available somehow, I think you'd find a lot of uptake from...
Yes, I mean a lot of people have used a box model in the past with UKCA, and anything you can do away from the queues will speed up the development process.
Yeah.
Because turnaround can be a really limiting factor when you're debugging or want to find out just what happens in simple circumstances. It's a useful thing to do.
And I think once the system model is frozen and released, there's actually more time for people to think about useful tools. I think a lot of our effort, especially in the Met Office, everybody's effort there in the past year or more has been getting the air system model ready. That's been, once that's through, that's a big horizon that's passed, and we've got more time to think about other things.
But don't forget the ticket business, because I have fear of people doing the same thing twice. And I mean, I did my PhD at Sutton Bonington, and there was agriculture and botany or something, and two of the researchers were chatting one day, and they discovered they were doing exactly the same PhD. And their professors didn't talk to each other.
I mean, in fact, tutorial 11 in the tutorials covers making a change for the trunk and row stem testing and things like that. So while you might not be able to run row stem on Archer, you can look at the row stem output and have a look at what that looks like. And if you have a monsoon access, you could do that there. If you have a virtual machine, you could do that on there. So there are.
RowStem is such a powerful tool, and is kept up to date.
Yeah. Yeah, if your jobs pass RowStem, they will pass in a climate model. That's the whole point. And if you write something new, you can add it to RowStem, and then it will protect it from other people breaking it accidentally, which is a big risk with a model like the UN with a million ones. So, well,
Okay,
that's great. We've actually finished on time. Well, that's perfect. You're one of the few to finish on time. Thanks, Colin, again.